So today I'm going to talk about an exploit we developed beginning of this year for IE 11. And since we were targeting the latest version of Windows 10, we had to bypass quite a few mitigations. So in the end, what we did is we submitted all the vulnerability details and all the used techniques to Microsoft's Mitigation Bypass Bounty program. And I'm quite happy to say that this was really the right decision because they awarded us with $100,000 for our submission. So in today's presentation, I'm now going through all the used techniques and vulnerabilities which were part of our submission. So we will start with a small motivation why we actually started developing the exploit in the first place. And after that, I will dive directly into the technical details. So we will start with the typed array neutering vulnerability, which is the bug we wanted to exploit to initially get code execution. I'll talk about IE's custom heap and how we misused that in order to turn the bug into a read-write primitive, which then allowed us to read and write the whole address space. Afterwards, I will talk about God mode, which is a known technique, which was previously mitigated by Microsoft, and I will show how we were able to re-enable that technique and basically execute code. And once we got code execution inside the browser, I will show you how we actually used the logic-based vulnerability to escape the EPM sandbox of IE 11. And finally, I'll talk about how we disabled Emmet as well. And before we're going to the conclusion, I will show you a small demo of the whole exploit. So who am I? My name is Moritz Jodeit. I'm the Director of Research at Bluefrost Security, which is a security company in Germany with a strong focus on vulnerability research. And my areas of interest are mainly low-level application security. So stuff like reverse engineering, bug hunting, exploitation techniques, and mitigations as well. So why did we actually start developing the exploit in the first place? Our goal was initially to participate in Pwn2Own this year. So we were thinking about which target we should choose, and based on the previous year's rules, we decided to go after IE 11. And this was mainly because I had some prior experience with IE 11, but also based on the expected difficulty versus the expected price money, IE 11 seemed exactly right. So we were expecting to attack IE 11 in the 64-bit version only. And during the last contest, you also had to manually enable enhanced protected mode, which is their stronger sandbox, which is not the default on Windows. And the exploit had to work on the latest version of Windows 10. And also the latest version of Emmet had to be installed. Okay, so we basically started roughly beginning of this year to develop the exploit. And roughly a month later, we got code execution. So we were a bit lucky because we found a really nice vulnerability. And of course, we didn't have a sandbox escape, and we didn't have a way to bypass Emmet yet. But we got code execution, and we were really positive that we would make it for Pwn2Own. And just a few days later, actually, Pwn2Own published the rules. And it turns out, for the first time in history, IE 11 is no longer part of the contest. So we were pretty frustrated, to be honest, because we spent so much time and so much effort in developing that thing. So we were thinking about what to do with the exploit. And as I said, we decided to send it to Microsoft's Mitigation Bypass Bounty program, because we had to bypass quite a few mitigations. And yeah, as I said, this was a good decision because they awarded us with $100K. So let's talk about the vulnerabilities we used. So the typed array neutering vulnerability is the initial bug we wanted to exploit. In order to understand that bug, you have to know about two basic JavaScript concepts, which are web workers and typed arrays. So web workers are basically a way of having multiple concurrent threads of JavaScript executing in your browser. And there's a way how these workers can actually communicate with each other, which is message pathing. So what you do is you call the post message method, and you can specify a message you want to send. And there is an optional argument called the transfer list, which basically allows you to transfer the ownership of an object from your current context into the receiving context of another worker. So what happens in that case is that the object you are transferring the ownership from it basically disappears in the current context, so it's getting neutered. That's a technical term for it. And it appears in the receiving context. Typed arrays, I mean, most of you probably know about them pretty well because they are often used in browser exploits nowadays, just because they give you a really powerful primitive if you are able to corrupt them or to modify them. Because if you can actually modify the size and the raw data pointer in a typed array, you get the ability to read and write the whole address space, basically, which is pretty powerful. So the implementation of typed arrays, they are split into views and buffers. And the view can be seen like a typecast. So it defines the way how data is actually accessed. And the buffer is where the actual binary data is stored. So there are several subclasses like uint8 array or uint32 array. And the buffer is actually implemented in an object called the array buffer object. And you can't access that object directly. So you always have to use one of these subclasses to actually access the data in the buffer. However, you can get a reference to the buffer using the .buffer property. So before we actually talk about the bug itself, or before actually looking for bugs, it's always good to read up on what people actually used before, what people found before. Because by taking a look at fixed bugs or previous bugs, most of the time it's a pretty easy, nice way to find new vulnerabilities. And it also gives you a feeling for where people might have already looked for vulnerabilities. So if you take a look at Pwn2Own 2014, there were in total 2 Mozilla Firefox exploits. And interestingly, both of them were in the same area of the same functionality. So the first one exploited by GeoHot, the title of the vulnerability says out of bounds write through typed array object after neutering. And the second one, which was exploited by Yuri Edler, it says out of bounds read write through neutering array buffer objects. So it looks like the whole concept of array buffers and the neutering process of the underlying array buffers seems to be really complex to implement. So I was interested in if IE11 actually had issues with this as well. And it turns out yes, they have. So this is the proof of concept or the trigger for the vulnerability. It's pretty simple. So first what we do is we create a new worker. So empty.js is just an empty file. So it's just an empty worker. And then we create a typed array, an int8 array in this case. And what we do then is we use a post message call to actually transfer the ownership of the underlying array buffer of the typed array to this worker. And as I said before, what happens in that case is this object, so the array buffer, gets neutered. So that means it gets freed in the current context. The issue here is that Microsoft actually forgot to invalidate this reference. So after a few milliseconds, if you continue using the typed array, you will actually access the freed array buffer. And there are actually some nice properties about this bug. So one of them is by specifying an index here, you actually have precise control over where in the freed memory you want to read or write. And here in this case we write, but we can also read. So if you enable page heap, for example, you get this nice crash. And you can see the index we used can be found in ESI, and the actual value we are storing can be found in the EAX register. And not only is this a nice bug because you have precise control over the freed memory or the memory which then might get reallocated with something else, but compared to other use of the free bugs, this is nice because usually what you have is in another use of the free bug, you have some object which gets freed, and then you try to reallocate it with another object of the same size. In this case, we actually control the size of the freed array buffer. So if we know there's a target object we want to corrupt, for example, of a certain size x, we just create a typed array of exactly this size, which will then create an array buffer of the same size, and then we trigger the bug, and then we have a free heap chunk of exactly size x. So we just try to allocate this target object, and we can actually modify modify it at will. So it's a pretty powerful bug. So how do we actually turn that into code execution? So first of all, in order to find some interesting object, you have to see where the memory is actually allocated. So if you take a look at the JS-JavaScript array buffer create function, you will see that they use the malloc function to allocate the memory. So that means the memory is allocated on the CRT or on the process heap. And this actually reduces the number of potentially useful objects because most of the interesting stuff, which you might want to corrupt, for example, like normal arrays, typed arrays, strings, whatever, they are allocated on IE's custom heap instead. So the question is, which object could we target in this case? There's one object called the large heap block object, and this object builds the foundation for IE's custom heap. And it turns out there's a pretty easy way how you can actually force the allocation of these objects. And what you can do is you just create many large array objects in JavaScript. So the code below will actually create several large array objects, and we store some integers in them. And this will actually create large heap block objects on the CRT heap. There's one thing to note here, which is, in this case, we store integers. If we store something else, like object references or JavaScript object references, the size of the allocated large heap block object will be different. Just keep that in mind because we make use of this fact later on in the exploit. So if you take a look in the debugger and you run the JavaScript code from the previous slide, you will see all these allocations of B8 bytes. And if you take a look at the memory of one of these allocations, you will actually see that these are really the large heap block objects we are looking for. So let's take a look at the structure of these objects. So there are several interesting fields. So at offset 8, there's a pointer to IE's custom heap. So if we do it like on the previous slide, like we use several large array objects, this pointer will actually point to the content of the array, which is stored on the custom heap, which is pretty useful, as we will see later. And there's a forward pointer and a backward pointer at offset 58 and 60, and I will talk about these on the next slide, why these are useful. And finally, at offset 70, there's a pointer to the current object, which is pretty nice because by leaking that pointer, you get to know the current address of the large heap block object you're operating on. So how do we actually turn this into some kind of useful primitive? So it turns out during garbage collection, the code will walk over all the large heap block objects. And it will, on every object, it will call the operator method. And what that method does is it will actually check if the forward and the backward pointer, which I previously mentioned, if these are set and not set to null, it will perform a doubly linked list unlink operation. And now you would think, okay, in the latest version of IE 11 on Windows 10, this is probably protected like in every modern heap allocator implementation. But it turns out it is not. So it's just a simple unlink operation. And you can easily overwrite the forward and the backward pointer, and you get a nice write 4 or write 8 primitive in this case. Of course, there's this small constraint that the written value, so the backward pointer, has to be a valid pointer because it's dereferenced in order to store the forward pointer afterwards. But effectively, you get the ability to store any pointer at an arbitrary address in memory. So this is nice. However, we want something more, right? So we want the ability to actually read memory, write arbitrary memory, and we also want to leak arbitrary JavaScript object addresses. And as I said before, typed arrays are pretty useful for doing this. So you just overwrite the size field and the raw data pointer. The issue here is, first, we need to find such an object in memory. And these objects are actually allocated on IE's custom heap. So only the underlying array buffer is actually stored on the CRT heap. So the question is, how do we actually find one of these objects? So this is the strategy. So what we do is we create two groups of typed arrays. So the first group has a certain size, and the second group has a different size. And then we trigger the bug on all of these typed arrays. So we have lots of typed arrays pointing to freed memory regions. And then we alternate between creating large arrays of integers and large arrays of object references, of typed array references. And eventually these will force the creation of large heap block objects, which will be placed in these free heap chunks. So to make it a little bit more easy to understand, here's a small demonstration. So on the left side, you have the CRT heap. On the right side, we have the custom heap. So first, we create the first group of typed arrays. And we make them exactly B8 bytes large. And as you can see here, the typed array is allocated on the custom heap, but the underlying array buffer is allocated on the CRT heap. So now we create a second group, but this time we use a different size. So we use the size A0 in this case. And again, the same stuff happens. So the array buffer of A0 bytes will be allocated on the CRT heap. So now we trigger the bug. So we have this scenario. So we have several typed arrays pointing to freed memory. So what we do now is we start to alternate between creating these large array objects. So first we create a large array object where we store integers. And this will eventually create a large heap block object on the CRT heap. And since we were storing integers, the created large heap block object will be exactly B8 bytes in size. So eventually, the large heap block object will be allocated in one of these 3 heap chunks we created before. Then we continue, and we create an array of typed arrays. And as I said before, depending on the value you are storing in the array, the large heap block object will have a different size. So in this case, it will have the size A0. And now you can see why we actually created the second group with size A0, because we have some 3 heap chunks where this large heap block might be placed into. So now we just continue, do the same thing again, create another integer array. And now you can see at the bottom right, this is exactly the memory layout we are looking for. So what we want to have is we want to have an integer array at the top, an integer array at the bottom, and in between we want to have an array of typed arrays. And one of the reference typed arrays should also reside between these 2 integer arrays. The nice thing is, of course, you can't reliably always create this memory layout because there's randomization and stuff. But there's an easy way of how you can actually figure out if you created this memory layout. And if you find out that you actually didn't manage to create exactly this layout, you can just retry and retry until you really succeeded in creating it. So the first step is to actually corrupt the first integer array. So how you do that? First, you have to find the address, of course. So we just use one of our typed arrays, and we read the pointer in the large heap block object, which points to the IE's custom heap. So we find out the address of this integer array. And afterwards, we trigger our write8 primitive. So we override the forward and the backward pointer of this object, and we trigger garbage collection. And what we do is we override the reserved length field of this array with a pointer. So effectively, we are increasing it by a large amount. So a quick refresher on how array objects are actually stored in memory. So there are actually 3 length fields. So the first one highlighted in red here, these are the number of allocated bytes. Then we have the array length, which is just the number of currently stored elements in this array. And we have the reserved length, which is basically the maximum number of elements you can store in this array. So if you try to store more elements, the array has to be reallocated. And we are overwriting the blue field here, the reserved length field. And this gives you the ability to write out of bounds. So you can write to memory after the array in memory. However, you can't read. So a nice trick is to just write somewhere out of bounds. And if you do that, the array length will be adjusted automatically. So we do exactly this in the second step. So we use the first integer array where we corrupt the size field, and we calculate the difference, the distance from this integer array to the first element of this one. And then we use the corrupted integer array to write into this element. And this has a nice benefit that we can actually check that the write operation succeeded, because we can easily check that the first element changed. And after we did that, we can basically read and write all the memory between these 2 integer arrays. So In the next step, we want to actually modify a typed array. So what we do is, again, we use the corrupted integer array, and we read all the pointers stored in the array of typed arrays. And for every pointer, we actually check if it points between our two integer arrays. And if it does, we know that we can actually write into this memory region, and we just calculate the distance and overwrite the size field and the raw data pointer. So then we have a typed array where we can, which we can use to read and write arbitrary memory in the process. Since we are targeting the 64-bit version, there's a slight issue here because you can only write certain integers using an integer array, so you can't write integers larger, 7f, but you can easily work around that, and there's actually a description on how to do that in our paper. So to summarize now, we have the ability to read and write arbitrary addresses, arbitrary memory in the process, and we can also leak arbitrary JavaScript object addresses. So if you go back, you can actually store any JavaScript object in this array of typed arrays, and then use the corrupted integer array to read this pointer, and you get the address of your object. So the question is, what do we do with this now? So we can read and write all the memory. So in the past, what you do, you would probably just leak the address of any JavaScript object, and you would overwrite the vtable pointer, and then you would trigger a function call and get code execution. However, on the recent version of Windows, you have control flow guard. So it's no longer possible to just overwrite any indirect function calls and immediately get code execution. So you either have to bypass CFG in a way, or do something else. And we actually decided to do something else. So let's talk about God mode. God mode is an attack against IE script interpreter engine. And it basically allows you to instantiate and run unsafe ActiveX controls. So as I said before, it's not a new technique. It was previously presented by Yang Yu and Yuki Chen in 2014. And what you could do is there's a single flag in memory called the safety option flag. And if you are able to overwrite this flag with a single null byte, you were actually able to instantiate and run ActiveX controls, which would then give you the ability to execute code, of course. So in IE11, there are two functions, namely script engine can create object and script engine can object run, which are used for deciding if it's possible or not. So when this technique was published, Microsoft tried to do something about it. And what they did is they introduced some kind of a 20-byte hash code. And the goal of this mitigation was to try to prevent people from just having to write a single null byte and enable the ability to execute code. There's a nice documentation of the whole thing in a blog post by Fortinet. However, there were still ways on how you could bypass that. So, for example, in Yuki Chen's xblib2 library, he implemented a nice, really elegant bypass of that mitigation. So what he did is he basically built his own security manager object in memory from scratch. So he rebuilt all the vtable pointers and everything. And then the only difference was he replaced two vtable function pointers with some rob gadgets which he dynamically found in memory. And then he replaced the reference to the security manager in the script engine object to his fake security manager, which effectively allowed him to instantiate and run ActiveX controls without touching the safety option flag at all. This worked nicely until CFG was introduced. So the way it was implemented in xblib2 didn't continue working when CFG was introduced. It's probably not too hard to adjust the code or to modify the code to make it work again, but we found out there was a much easier way to actually do it. So when I did the analysis, my goal was to actually find the code where the hash is calculated and where the hash is compared, because I wanted to see if there's maybe a way how you can bypass this mitigation. And I was looking around and comparing functions and looking for these kind of protection functions, and I just couldn't find these functions. And in the end, I thought, okay, I must be stupid, I must be overlooking something. So what I did is I just tried to overwrite the safety option flag, and it turns out it just worked. So I was a bit confused because it appears this mitigation, it just disappeared in the latest version of Windows 10. So later on I found out that actually this was only the case for Windows 10. So I did all my analysis on Windows 10. So in Windows 8.1, for example, the mitigation was still there. And interestingly, I was talking to someone at CanSec West this year from Microsoft, and they told me the mitigation actually disappeared due to an internal compiler change, which I found quite interesting. So in the end, what you could do is you basically just leak the address of the script engine object, and you write a single null byte to this address, and afterwards you can instantiate any ActiveX controls you like. So in this case, I instantiate WScript shell, and I can just execute Notepad, for example. So this gives you immediate code execution in the browser. However, as I said before, we are targeting IE11 with EPM, the enhanced protected mode, so there are stronger sandbox enabled. So although we can execute any commands, they are executed within the browser sandbox. So let's see how we can escape that sandbox. Again, I was reading up on old techniques used by other people, and I found this nice way of how people actually escape the protected mode, so the less secure version of the sandbox, which is based on zones. So zones are basically an IE11 concept or an IE concept where you can apply security settings to different groups of sites. And interestingly, when IE renders a page which is considered to be part of the intranet zone or the trusted sites zone, the page will be rendered outside of the sandbox. So yeah, any page which is considered to be part of this zone will be rendered outside of the sandbox in a 32-bit process with medium integrity. This was actually first documented in Verizon's IE protected mode paper in 2010. And the basic idea is, so you trigger your exploit, you get code execution in the browser, and then in your first stage payload, you load a web server. And using this web server, you deliver your same exploit again. And then you redirect IE to your local host, basically, which will then render the page in the local intranet site zone. So it will be rendered outside of the sandbox. And then you basically trigger your same exploit again, and you get code execution outside of the sandbox. So it's a pretty neat technique. And it was previously exploited several times. I mean, like the Verizon guys, they exploited it. The ZDI guys, they exploited it in their Pwn for Fun contest in 2014. And they actually reported the issue to Microsoft. And it's quite interesting to take a look at the advisory, because this issue was actually never fixed. So the advisory contains a response from Microsoft which says does not meet the bar for security servicing. This is because, at least in the past, protected mode wasn't considered to be a security boundary. But Microsoft gives a recommendation in their response how you can actually mitigate the issue. And the recommendation is to enable enhanced protected mode, so the sandbox we are trying to attack now. And why does EPM actually protect against this issue? So EPM is based on the app container sandbox, which is a really strong sandbox on Windows. And what app container does is it provides network isolation. And network isolation basically prevents a sandbox process from accepting new network connections, and it also should prevent the sandbox process from establishing new connections to the local machine. So if we step back for a second and think about it, we are not really limited to localhost, right? So all we want to have is we want any domain name which is somehow considered to be part of the local intranet zone, and that should be enough if we can deliver our exploit using this host name. So we were reading up on how IE actually decides if a site is part of the local intranet zone, and it turns out there are several rules. So one of the easy ones is called the plain hostname rule. And basically what it says is if the domain name doesn't contain any periods, the site is automatically mapped to the local intranet zone. So the question is, how can we actually create such a domain name which points to our external IP address? And it turns out we can use local NetBIOS name spoofing for that. So as far as I know, local NBNS spoofing was first implemented in Foxglove's hot potato exploit. and it was used for the purpose of local privilege escalation. So NBNS or NetBIOS name service is a UDP-based protocol, and it's basically used as a fallback mechanism once DNS fails. So if you do a DNS lookup on Windows and you don't get a response, at some point Windows is sending out these UDP packets. And these packets actually have a 16-bit transaction ID, which is used to match the request packet to the corresponding response packet. So in order for a response packet to be accepted, it has to contain the same transaction ID as a response packet. And in a normal NetBIOS name spoofing scenario where you're sitting on a network and listening for new packets, what you do is you just use one of these response packets, you extract the transaction ID, put it into your response, and send your fake response packet. However, in the local scenario, we don't see these outgoing UDP packets. So we can trigger them easily, but we don't see these packets. So we can't really find out which transaction ID to use. However, as it turns out, it's quite easy to just brute force them. So you just trigger one of these requests, and then you flood the local machine with lots of NBNS response packets, and you iterate through the whole range of possible transaction IDs until you find the right one. And this gives you the ability to actually register a new domain name on Windows. So this is a sample packet, so you can see the transaction ID is stored here, so it's a request packet for the domain name Bluefrost. And if you listen carefully until now, you might think this would not be possible from within the sandbox, because there's this thing, the network isolation thingy, which should prevent you from actually sending packets to the local machine. However, there is an exception. So it's actually possible to send UDP packets to the local host on port 137. So in the end, this allows you to do local NetBIOS name spoofing from within the app container sandbox. So what we did is, once we got code execution, we start doing local NBNS spoofing. We register a new domain name, which doesn't contain any periods. And then we redirect IE to this new domain name. So now it's considered to be part of the local intranet zone, and we just deliver the same exploit, but this time for 32-bit, and exploit it again, and now we got code execution outside of the sandbox. So now let's take a look at Emmet, because we were aiming for pwn2own, so we also had to bypass Emmet. Since we didn't use any kind of ROP gadgets or shellcode until now, the question is maybe Emmet doesn't detect us at all. So let's take a look. It turns out Emmet detects the exploit, and especially the attack surface reduction or ASR feature of Emmet will catch us. So what ASR does, it's basically a blacklist of certain modules which are considered to be dangerous, and they hook the load library X function. So every time a new module gets loaded, they will actually check the name of this module against their blacklist, and if it's part of that blacklist, they will terminate the process, basically. And in our case, they detect the loading of the WScript shell module. So again, I was reading up on old techniques, and there's actually a nice blog post by FireEye where they presented their latest way of how they disabled Emmet. And they have a pretty good list of all the prior work and prior publications on how people disabled or deactivated Emmet, basically. However, compared to most of these techniques, we have a little different scenario here, because we actually don't have the ability to execute code before we actually disable Emmet. So since Emmet is detecting the loading of an ActiveX control, which we then want to use to execute code, we can't use any ROP gadgets, for example, to disable Emmet. However, we have a really nice and powerful read-write primitive. So let's see if we can maybe use that in order to turn off Emmet. So if you take a look at the Emmet 64 DLL and you're looking for the ASR code, you will find this small snippet of code here, which is just before the actual Emmet. Okay. Cheers, man. All right. So, yeah, talking about ASR. So, this is actually the code which is just in front of the actual ASR check. So what it does is it reads a pointer from a static location in the emit module, which is an encoded pointer. So they do a decode pointer call to decode it. And this pointer actually points to the config structure on the heap, which we call config struct. And this structure has a pointer we call enable protection pointer, which points to some flag in memory, which actually decides about if the ASR check should be performed or not. So the idea here was to maybe we can just overwrite this flag. Actually, it's not quite that easy because the flag is stored in memory, which is marked read-only. So they thought about that. So the next thing we thought about, maybe you can just overwrite the enable protection pointer and point it to some memory which happens to contain some null bytes. This is possible, however, you need to find the address of this config struct in memory or on the heap. So as I said, there is this pointer at a static location in the module. However, it's protected with a call to encode pointer, which is a Windows API to obfuscate pointers in memory. So let's take a look at the MSDN documentation to see what that actually means if a pointer is obfuscated. So they say the encode pointer function obfuscates the pointer value with a secret value. And this secret value is actually different for each process. So this implies the secret is actually the same for the same process. So the idea here was maybe we can use our read-write primitive to leak this pointer and then basically do the deobfuscation on our own using the secret value. So we were looking into the implementation, which can be found in RTL encode pointer and RTL decode pointer, respectively. And it turns out they use a 32-bit secret value, which is, by the way, also the case for the 64-bit version of Windows. And they get that directly from the kernel. So they just do a ZW query information process call, get the secret value, use that in their calculation, and then basically throw it away. So I didn't see a way of how you could actually use a read primitive to leak that value. However, let's take a look at the implementation of these two functions. So this is some pseudocode for the encode pointer and the decode pointer API on the 64-bit version of Windows. And as you can see, what they do is they take the plain pointer, they XOR it with the secret value, and then they do a rolling right shift, which again depends on this secret value. And they probably did that in order to prevent some simple XOR attacks, because if the right shift wouldn't depend on the secret value, what you could do is you would just take a plain pointer, the corresponding encoded pointer, you could XOR them together and obtain the secret value. So it's not that easy. However, the number of bits this value is right shifted there are actually only 3 possible values. So it can be brute forced. So what we do is, first we take a pair of pointers. So we take a plain pointer and the corresponding encoded pointer, and we perform a partial decode pointer operation. So here you can see we iterate through all the 3 possible right shift values. Here we perform a partial decode operation, and then we XOR the result with the corresponding plain pointer, which gives us a potential secret key. It doesn't have to be the right one in this case. So then what we do is we perform the encode pointer operation in JavaScript, and we use this key, which we found, in order to encode this plain pointer, and we check if the result is actually the expected encoded pointer. And if it is, then we assume we might have found the right key. However, there's a small problem here. So there can be cases where we get a secret key collision. And this is because if you take a plain pointer and you encode that with 2 different keys, it can happen that you get the same encoded pointer for both keys. So this isn't a problem if you're using the API as you should, but since we are basically doing it backwards, it can happen that we actually get a wrong key. And obviously this is bad because if we use the wrong key to deobfuscate a pointer, we get a wrong pointer and we just crash. So in order to bypass that, we just use a second pair of plain and encoded pointers. So once we found a key which we think is the right one, we try to encode the plain pointer with this key and check if the corresponding encoded pointer matches. So if it does, we can be pretty sure that we found the right key. So this gives us the ability to actually deobfuscate any pointer in the current process. So as I said, you need a plain pointer and the corresponding encoded pointer. But it turns out this is quite easy. So in theory, you could look into any module which is currently loaded, which is using the encode and decode pointer API. We concentrated on the emit module itself. And as you can see here, this is just one case where they basically call encode pointer on the null pointer. So the plain pointer is the null pointer, and then they store the result at some static location in the data segment. So once you leak the base address of emit64, you can actually just read the encoded pointer, and you have your first pair of plain and encoded pointer. And finding more of these pairs is actually quite easy, so you just look for these encode pointer calls. And in our white paper, there's another example of another pair, how you can easily find that. So as I said, with these pointers, you are now able to calculate the secret of the current process, which gives you the ability to deobfuscate any pointer in memory. So what we do now is, first we leak the base address of emit64. In order to do that, what we do is we just take a look at, we just read the memory of one of these functions which is hooked by emit, because emit is hooking several functions in memory. So for example, you just read the first few bytes of the anti-protect virtual memory function, and what you do is you basically just follow pointers until you find the base address of emit64. And once you found that, you will actually read this pointer to the config struct. We deobfuscate the pointer using the secret value, which we previously calculated. And then we just override the enabled protection pointer in memory. And we just point it to some memory location which stores some 0 bytes. So this is enough to actually disable emit completely. Or this actually disables the ASR check, but I mean, you can do the same stuff in order to disable other emit checks as well. So this basically gave us the possibility to execute code outside of the sandbox, and we successfully disabled emit as well. So before I'm coming to the conclusion, I'll show you a quick demo of the exploit. So first, we have a look at the version of IE11 we are running here. So this was the latest version of IE11 when we developed the exploit. And then we have a look at the settings, because as I said before, we changed some of the settings in IE11 to make it more secure, basically. So what we did here is we enabled the 64-bit processes for enhanced protected mode. And we also enabled the enhanced protected mode itself. So now we have a look at emit, which is installed on the system. And as you can see, this is the latest version of emit, still as of today, by the way. And the only setting which we changed here is the early warning check. Because what that does is, once emit finds an exploit, it will actually send some information to Microsoft. And we obviously didn't want to happen that in this case. So now we are launching the exploit. So now you can see the renderer process here. It's actually consuming some CPU time because now it's doing all these allocations. And as you can see here, the integrity level is app container, so it's still inside, it's running inside the sandbox. So after a while, you will see that a new process gets spawned. There you go. So this sandbox escape EXI is a binary which we dropped on the machine and executed. And as you can see, the integrity level is still app container, so this binary is still running inside the sandbox. And if you wait a bit, you will actually see that the URL changes. This is because now we are trying to register a new domain name called Bluefrost. We redirected IE to this domain name, and now we try to exploit the same bug again. And as you can see, a new renderer process got spawned, which is now running with medium integrity level. So this is running outside of the sandbox. So now it takes some time to do all the allocation stuff again, and eventually, if this exploit succeeded, we have now some notepad which is running with medium integrity level, so it's running outside of the sandbox. Thank you.
Casi. Bien. Fede, Leo, ¿preguntas, chicos? ¿Nadie?
I actually have a conclusion as well.
Ah, bueno. Vuelvo. No dije nada.
So, yeah, my conclusion. My conclusion is gone, it seems. Yeah. So I just wanted to talk, before my conclusion, I wanted to talk about the current patch status. So actually the typed array neutering vulnerability, so the bug which I exploited initially, it was fixed in MS 16063. And interestingly, the same bug was already fixed in the Chakra core engine, which was published on GitHub. And it was fixed since the beginning. It was published on GitHub. So this looks like the bug which was patched by Microsoft before, but maybe they forgot to backport a security fix in this case. The EPM sandbox escape using local NBNS spoofing, it was fixed in MS 16077. And the God mode technique, where you can write a single null byte, this was fixed in MS 16051. And what they did is they introduced, instead of using this 20-byte hash thing, they got rid of that, and instead they are now using the query protected policy API, which is a Windows API which is exactly used for this purpose, to protect certain areas of memory which are considered to be critical. And interestingly, the God mode fix only applies to processes running inside the sandbox. So for every renderer process which is running outside of the sandbox, you can still use the technique, write a single null byte and get code execution. And finally, the emit bypass is not fixed at all, so they decided to not fix that. So all the techniques I've shown you today, you can still use them in the latest version of emit to turn it off, basically. So my conclusion, of course, all these new exploit mitigations, they make it quite challenging and increase the effort to write stable exploits nowadays. However, depending on the vulnerability you have, you might still be able to bypass many of them. And one thing I wanted to note here is many people tell me, yeah, once all these CFG protections and all these CFI solutions are in place, and you can't override indirect function calls anymore, exploitation is dead, right? So it's not really that control flow hijacking is a necessity. I mean, people, of course, used it in the past because it's easy. You just override EIP or RIP and execute your shellcode and do your thing. But if you have a read-write primitive, this is so powerful. You can actually do so many things without gaining of the control flow of the program. And you can do all kinds of things which you need. And in general, data-only attacks can also be used to bypass many mitigations as well. Because you can target so many functionalities inside the program, inside the current process, basically. So, of course, there's obvious functionality like loading unsafe ActiveX controls, which just shouldn't be inside your current process, right? Because you can just enable that. And another example is, for example, if you take a look at Firefox, there you have the possibility to execute JavaScript code at Chrome context. And what that does is basically it allows you to execute JavaScript code which has full access to the operating system. So you can still read and write files, execute commands, all that stuff. So this is obviously something dangerous to have in your code. But there are other functionalities which are not quite that obvious, which you can still target and turn them to your advantage. And just my personal opinion is that I expect to see more and more data-only attacks in the future, especially once all those CFI solutions mature and all these easy bypasses, which are nowadays still possible. Once they are fixed, I think more and more people will actually target certain important data structures in the process without trying to override function pointers, for example. So there are some references of the work which I used. And yeah, now I'm done. Thank you. Gracias.
¿Preguntas?
Yo quiero preguntar, pero me da miedo, te veo apurado.
Para nada, es la primera eco que me sobra tiempo, boludo.
Thank you. Amazing presentation. Question. You said that the God mode is not over. When I is in intranet mode, you said something like that? Like if you're in intranet, you can still use the God mode?
Yeah, I mean, what they did is they fixed the issue for rendering processes running inside the sandbox, which in my opinion is the most important thing to fix. But once a renderer process is running at medium integrity level, the same technique still works. So if you're targeting some internal guy, for example, and the page is rendered inside the local internet zone, then you can still use the technique, yeah, right?
Okay, but that has nothing to do with the worker bug. The worker bug it's over, right?
Yeah, this one is fixed, yeah.
Okay.
Yeah.
Thank you.
¿Alguna otra pregunta? No sé si veo las luces o veo manos. Bueno, entonces vamos a dar... A ver, ahí tenemos. Vamos a correr. Levante la mano de vuelta. Ahí va.
Hi, thanks. To find the initial bug, did you use an already found one? Or did you use a fuzzer? Or did you just follow the code?
Actually, I can't really say it was a fuzzer. I mean, I was looking at these old bugs and was more or less playing around with it. I did some kind of script, but you can't really call it a fuzzer. And this gave me the typed array neutering bug, yeah.
¿Alguna pregunta? Última oportunidad. Bueno, un fuerte aplauso.